We can use truth tables to assess the logical properties of sentences. To see how that goes, we need to introduce a few new semantic concepts. The first new semantic concept is the concept of a tautology. A tautology is a sentence that is true on every valuation. You may remember that every row in a truth table for a sentence represents one of the possible valuations of that sentence. And that means that the truth table of a tautology contains only t's in the column under the main connective of that sentence. So for example, the sentence A or not A is a tautology. Here at the bottom of the slide, you see the truth table for this sentence. Since we have only one atomic sentence, A, this truth table has two rows. And we see that not A is false when A is true and true when A is false. And given that a disjunction is true if and only if one of its or both of its disjuncts are true, it follows that the disjunction A or not A is true in every row of this truth table. In the first row, it is true because the first disjunct A is true, and in the second row, it is true because the second disjunct not A is true. So no matter the valuation of A or not A is a true sentence, and that means that this sentence is a tautology. Our second new semantic concept is that of a contradiction. A contradiction is a sentence that is false on every valuation. And that means that the truth table of a contradiction contains only f's in the column under the main connective of that sentence. For example, the sentence A and not A is a contradiction. Here you can see the truth table of this sentence. First, you will notice again that not A is false when A is true and true when A is false. Now, a conjunction is true if and only if both conjuncts are true. And since there's no possible valuation on which both A and not A are true, it follows that the conjunction A and not A is false on every possible valuation. And this is represented in the column under the main connective, which is the conjunction sign. You can see that this column contains only f's, and that means that the conjunction A and not A is a contradiction. It is false on every possible valuation. Our third new semantic concept is that of a truth table contingent sentence. A sentence is truth table contingent just in case it is true on some, but not on all valuations. That means that the truth table of a truth table contingent sentence contains some t's and some f's in the column under the main connective of that sentence. For example, the sentence A and B is truth table contingent. Here I've just reproduced the characteristic truth table of the conjunction sign, and you will see that this truth table contains some t's and some f's in the column under the conjunction sign, and that just means that the conjunction A and B is truth table contingent. You may have noticed that knowing what the main connective of a sentence is crucial for analyzing its logical properties. And that's why I would like to give you a more explicit strategy for identifying the main connective of a sentence. you can reliably identify the main connective of a sentence in 4 easy steps. First, if the first symbol in the sentence is a negation sign, then this negation sign is the main logical operator, or in other words, the main connective. Now, otherwise, if the first symbol is not the negation sign, start counting the brackets. For each opening bracket, add 1, and for each closing bracket, subtract 1. At the point when your count is at exactly 1, the first operator you hit, which is not a negation sign, is the main logical operator. Now, it is thereby important that you include all the brackets in the sentence. So that means that in order to apply the strategy, you cannot omit any brackets as we allowed when we introduced our bracketing conventions in the last lecture. So in particular, you always need to include the outermost brackets that go around the entire sentence. To see how this works, let's look at an example. So here we have a sentence, and our task is to find the main logical operator. The first thing that I am going to do is I am going to add the outermost brackets, since that is important for reasons that I just explained. So we can't omit the outermost brackets around the sentence. And now I'm going to start counting brackets. I start at the very left and I count 1, 2, 3 for the first 3 brackets here. Now I count 2, 3. Next, I see 1 closing bracket, so that reduces my count to 2. I see another closing bracket, which reduces my count to 1. And now the first connective that I see when my count gets to exactly 1 is this conditional here. And that means that the conditional is the main connective. So we have introduced a number of new semantic concepts. Let's relate these new concepts to the old concepts that we have already encountered. In our very first lecture, you may remember that we learned about necessary truth. A sentence is a necessary truth if and only if it is true in every possible scenario. Now, this concept is closely related, but also importantly different from the new concept of a tautology. In particular, every tautology is a necessary truth, but some necessary truths are not tautologies. For example, the sentence 2 plus 2 equals 4 is a necessary truth, but it is not a tautology. Why is it a necessary truth? Well, we said all mathematical truths are necessary, given that their truth does not depend on what the world is like. And so, since 2 plus 2 equals 4 is a mathematical truth, it is a necessary truth. However, this sentence is not a tautology, as we may find out when we construct the truth table of this sentence. Now, 2 plus 2 equals 4 is an atomic sentence. So I'm going to symbolize this sentence by means of a TFL symbol, namely the capital letter A. And now we know that when we construct a truth table for just one sentence, for just one atomic sentence, this truth table is going to contain 2 rows, one for each of the possible valuations of our atomic sentence. And so our truth table for the sentence letter A contains 1 row in which this sentence is true and 1 row in which this sentence is false. And so since this truth table contains a row where the sentence is represented as false, it follows that this sentence is not a tautology. So some sentences are necessary truth, but not tautologies. For example, 2 plus 2 equals 4 is a necessary truth, but not a tautology. Let's think a little more about why that is. What explains this? Well, the core explanation is that there are more valuations than hypothetical scenarios. So the situation looks a little bit like this. If this big circle represents all possible valuations, the hypothetical scenarios are a proper subset of that. So, for example, we know that in this case, the capital letter A represents the sentence 2 plus 2 equals 4. And we know that this sentence is a necessary truth and therefore true in all hypothetical scenarios. But we also saw that the truth table for the sentence A contains a row in which this sentence is evaluated as false. And that means that this row here does not correspond to a genuinely possible hypothetical scenario. Even though this row represents a possible valuation, it does not represent a genuinely possible hypothetical scenario. And so this shows that there are more valuations than hypothetical scenarios, which entails that there must be more tautologies than necessary truth. Or in other words, some necessary truth are not tautologies. Let's compare necessary falsehoods with contradictions. You may recall that a sentence is a necessary falsehood just in case it is false in every possible scenario. In contrast, a sentence is a contradiction just in case it is false on every possible valuation. Now, every contradiction is a necessary falsehood, but some necessary falsehoods are not contradictions. So, for example, 2 plus 2 equals 7 is a necessary falsehood, but it is not a contradiction. And the reason is again exactly analogous to our previous example. 2 plus 2 equals 7 is a mathematical falsehood, and assuming that every mathematically false sentence is necessarily false, it follows that this sentence is a necessary falsehood. But if we construct the truth table for that sentence, it is going to contain a row that represents it as true. This sentence is an atomic sentence, so we are going to represent it by a capital letter A. And the truth table for the capital letter A is going to contain 2 rows, one in which it is true and one in which it is false. And that means that this sentence is not a contradiction, despite the fact that given our interpretation of the sentence letter A, it is a necessary falsehood. Finally, let's compare contingent sentences with true-stable contingent sentences. You may recall that a sentence is contingent just in case it is true in some, but not in all hypothetical scenarios. In contrast, a sentence is truth-table contingent just in case it is true in some, but not in all possible valuations. Now, every contingent sentence is truth-table contingent, but some truth-table contingent sentences are not contingent. For example, as we just saw, the sentence 2 plus 3 equals 7 is truth-table contingent, but it is not contingent given that it is a necessary falsehood. Let's sum up what we have learned. In our first lecture, we encountered 3 important logical concepts. They are necessary truth, necessary falsehoods, and contingent sentences. Necessary truths are true in all hypothetical scenarios. Necessary falsehoods are false in all hypothetical scenarios. And contingent sentences are true in some, but not in all hypothetical scenarios. Now, in this lecture, we introduced 3 new semantic concepts: the concept of a tautology, of a contradiction, and of a truth-table contingent sentence. A tautology is true on every possible valuation, a contradiction is false on every possible valuation, and a truth-table contingent sentence is true on some, but not on all possible valuations. We also saw that whether a sentence is a tautology, a contradiction, or truth-table contingent can be read off the truth table of that sentence. And so we have a method for figuring out whether a sentence is a tautology, a contradiction, or truth-table contingent. Now that's progress. We found out a specific strategy and approach for determining some of the logical properties of sentences. But this method nevertheless has limitations. We saw that every tautology is a necessary truth, but some necessary truths are not tautologies. Similarly, every contradiction is a necessary falsehood, but some necessary falsehoods are not contradictions. And finally, every contingent sentence is truth-table contingent, but some truth-table contingent sentences are not contingent. That means that truth tables are very valuable. They offer important insights about the logical properties of sentences, but they do not do all for us. We still need to use reason and reflect on the meaning of sentences if we want to learn all of their logical properties. That was it for today. In the next lecture, we are going to go on and discuss a few more uses of truth tables for the analysis of arguments.